see, I will take a section over here. Then it gives me 2.5 into 2, that is of 5 kilonewton into meter. Sign convention is important for me right now. Take a section, left side, anti-clockwise nature. This is of hogging nature, as we studied previous classes of hogging nature, treated as negative. So this sign is of negative. So this ordinate gives me and joining by inclined straight line 5. Now let us take a section just right of C. So what I did, I will taking incorporation of this 10 kilonewton into meter within the calculation. Then in that case, see the figure, this is my given beam. I will take a section on the just right. So bending moment at C just right is equal to 2.5 into 2, negative sign, section left anti-clockwise, this section right clockwise plus 10. Remember, it is the given concentrated moment is given to us, hence it is plus sign, and this give you plus 5 kilonewton into meter, plus sign. So at the same section C, from minus sign to plus sign I have to go. Next, at B we know the value is 0, and between C and B there is no load. Variation is given by inclined straight line. This is straight line, this is also straight line, negative value, positive value, and this is our bending moment diagram. So what we learn from this diagram, carefully visualize. We learn from the diagram is that when a beam subjected to concentrated moment, the variation of BMD changes abruptly. Sudden change in bending moment diagram. Visualize carefully. See the diagram over here. This is the shear force diagram, and next this is our bending moment diagram. Now let us conclude from both this diagram. The first conclusion from this diagram: if a beam subjected to a concentrated moment, there is no effect of this concentrated moment on the shear force diagram directly at that particular point. Yes, it is obviously effect on the calculation of reactions, but there is no direct effect at that particular point, the point at which the bending concentrated moment acts. There is no effect on the shear force diagram. Next observation about this: bending moment changes abruptly at a location where concentrated moment acts. So with this, let us go with the next one problem. Yes, the given beam is of simply supported beam. The load which is acting on the beam is of UVL nature with two different triangles. Up to 4 meter, one triangle, after that 1 meter, another triangle. So the given load is of this nature, which is acting on a beam, and our intention is to plot shear force diagram as well as the bending moment diagram for this particular beam. As usual, the step number 1 for us: calculation of support reaction. So before we proceed the calculation of the support reaction, it is utmost important is to simplify the figure and convert it the UVL in terms of equivalent point load. Just see over here, half into 20 into 4. This 20 is the ordinate, so this is nothing but the area of triangle. Half into 20 into 4, which will act at the CG. The CG distance is 2/4. The another small triangle, the load is of half into 20 into 1, that is the area of triangle. Distance from A is 4 plus 1/3 into 1. Now with this figure, let us go for the finding out the support reaction. Yes, step number 1, sigma h is equal to 0. Refer the figure previous. No horizontal force is acting throughout the system, hence we will apply sigma h is equal to 0. RAH obviously comes as 0. Let us we use second condition, sigma v is equal to 0. So the first RAV, which is acting upward, so plus sign. The another load, that is the total load, triangular load, half into 20 into 5, area of triangle, plus upward RB is equal to 0, and we achieve RAV plus RB is equal to 50 kilonewton. How this achieve? Half into 20 into 5. So for that you have to refer the previous figure. Triangle is there, so half into 5, 5 meter is the total length, 20 is the ordinate, so area of triangle. Next, see these equations, RAV and RB, the two unknowns. Hence we required another third condition, that is sigma m at one specific point is equal to 0. Let us we take sigma m A is equal to 0. Now while taking a moment, I will divide my triangles into two different triangles. The reason behind is that CG parameter must be known for us. If you refer the previous figures, why I have divided these triangles into two different triangles, first and second? Because we do not know what is exact the CG of this particular triangle. I do not know the formula, or it is difficult for us to find out. So it's once again we have to apply mathematics. So what we did, what we have to do, we have to divide the triangles in a such a way that the CG of that triangle must be known to us. So CG for this triangle is known to us. So RAH, if we take the moment at this point is equal to 0, RAH into 0 it is 0, RAV into 0 it is 0, but this load half into 20 into 4 creates a clockwise moment at A, that is half into 20 into 4 into 2/4 creates a moment at A, that is a plus sign. Another force plus, because this also create clockwise moment, half into 20 into 1 into bracket 4 plus 1/3 into 1. This both creates clockwise moment, hence plus sign, while RB creates anti-clockwise moment at A, hence minus sign RB into 5 is equal to 0. See this equation, the same equations that have been spoken, equated with 0. By simplifying this, we achieve RB is equal to 30 kilonewton. We know the value of RB as 30 kilonewton. By replacing the value of RB in this equation, we achieve RAV is equal to 50 minus 30 is equal to 20 kilonewton. So step number 1, that is the determination of support reactions, are over for us. Next step is the plotting of shear force diagram. Now let us use the fundamentals. Let us use first the fundamentals and let us plot the diagram. Recall, we had solved the previous problem right now, that a beam subjected to UVL, the variation of shear force diagram is given by parabola, the parabolic nature. Now, how to plot? We know the reactions RA and RB. So first, reaction itself gives the ordinate for the shear force. So here the ordinate is of 20. Here the ordinate is of 30. Now the sign convention is of utmost parameter. Important one, section left upward plus 20. So this is upward plus. Now we know the variation. So now we have to find out what is the value at 1 meter, what is the value at 2 meter, what is the value of 3 meter, what is the shear force variation at 4 meter, what is the variation of shear force at 5 meter. At 6 meter it is known to us, that is of 30, which is of negative sign because section right upward treated as negative. So now we have to find out the shear force at 1 meter. Let us find out at 1 meter, 2 meter, and remaining you have to do by yourself. Let us go over here. This is of 20 kilonewton, this is of 30 kilonewton. Let us find out the shear force at 1 meter, that x is equal to 1 meter. So our figure look like this. Now this distance is of 4 meter, this ordinate is of 20, so we will use a logic of triangle. For 4 meter horizontal distance, if the vertical distance is of 20, then for 1 meter, this distance is of 1 meter. What is the ordinate? That is 1 into 20 by 4, that is of 5. So this ordinate is of 5 kilonewton per meter. So shear force at 1 meter is equal to, reaction is known to me, first is 20, section left upward positive sign. Now next, another is of this triangle load, that is nothing but the area of triangle, so minus half into 5 into 1. Why minus sign? Because section load is acting downward, left down. Once again, section over here, all the load vertical is downward, so it is minus sign. So we achieve 20 minus 2.5, 17.5 kilonewton. Now similarly found out at 2 meter. If we go for 2 meter, this is x is equal to 2 meter and this ordinate is of 20. Question may arise, how it is 10? Similarly, for 4 meter, if it is of 20, for 2 meter it is how much? 2 into 20 by 4, 40 by 4, it is 10. So shear force at 2 meter is equal to 20 minus half into 2 into 10, and this value is of plus 10. Similarly, we can find out shear force at 3 meter. We can find out shear force at 4 meter and shear force at the 5 meter. By plotting all these ordinates and then join all the ordinates, we will achieve, this is the shear force diagram. Now, very carefully visualized, while we plot this diagram, while we plot the ordinate at 1 meter is positive value, at 2 meter it is positive value, but at 3 meter and 4 meter the values comes negative sign. Means between 2 to 3 meter the ordinate changes its sign from plus to minus, positive to negative. Means at a certain point between 2 to 3 meter the shear force is 0, and we have to determine this location. Thus we found out the location. We found out one important point, that is x. We conclude that x is within the 0 to 4 meter range. So this is we found out. If for 4 meter the vertical ordinate is of 20, then for x it is how much? That is 20x by 4, that is of 5x. So this ordinate is of 5x. So we achieve shear force at xx is equal to 20 minus half into x into 5x, and nothing but 20 minus 5x square by 2. Intention is to find out the x equated with 0, and we achieve shear force at